Hi, my name is Jared Harrington, and this is my video on Lab 2 Motion of a Falling Object. I will begin by outlining this video. First, I will start off by briefly introducing this lab, then move on to talking about the physics principles, then discussing the experiment, the computational models and code, and then comparing and analyzing the computational models to the experimental model, and then finally concluding with the questions. So the purpose of this lab was to observe the motion of an object that was dropped from rest and falls slowly. Then we had to compare the results to a computational model that included the effect of gravity and then another computational model that accounted for the effects of gravity and drag force. Some physics principles that applied in this lab were Newton's second law, gravitational force, and drag force. So for Newton's second law, similar to lab 1, a force must be equivalent to the change in momentum over change in time. When there is a constant mass, this can be equated to force equals mass times acceleration. And then I have the equation shown right here. And then some other equations that will be used in this experiment are the velocity update formula and the position update formula. And then other physics principles include gravitational force, which near the Earth's surface is gravity is 9.8 meters per second squared. And then I have the equation shown here. And then drag force opposes the motion of an object and is proportional to the square of velocity. And the equation is shown right here. So for the experiment, I dropped the tennis ball starting at rest, and I dropped it and it fell slowly to the ground. The system in this case would be the tennis ball, and the surroundings would be the external forces such as gravity and drag force. So for this I recorded a video of me dropping a tennis ball and put it into the tracker app. And the observed position is shown. I got the change in time, the initial velocity, and then the mass of a tennis ball. And then here you can also see the graphs of the experiment. For the computational code, including the force of gravity, I included the time where the ball hit the ground. I updated the net force to be equal to the gravitational force formula, and then I included the velocity update formula and then the position update formula. For these two models, at the start, you can tell that they align, but as time continues, they start to separate, which indicates that there is another force being involved, and this force is drag force. Now for this computational code, which includes gravity and drag, I found B to be equal to 0.0689, and this was determined by plugging in values of B to get the predicted model to be equal, the final position of the predicted model to be equal to the final position of the observed model. And then I included the gravitational force, and then I had the drag force formula, and then I added those two together to get the net force. For the comparison of all three models, the drag force is better aligned with the observed position than the predicted position, but there is a degree of separation, which means that there were sources of error. So a big source of error would be with the tracking app, as within each frame I may not have aligned the center of mass of the tennis ball equally. And then also there was an element of wind while I was recording the drop. For the what does this mean question, to achieve terminal velocity, the net force must be equal to 0. And in the first graph, velocity curves until it reaches a constant value, which means that acceleration would be equal to 0, and thus net force would be equal to 0. For our what if question, if the object was initially thrown downward, would the terminal velocity be the same? In this case, it would be the same because in the left graph, I set the initial velocity for the y value to be -1, and it reached the terminal velocity at a sooner pace, but it still was the same value as in the right graph, which the initial velocity was equal to 0.